Thank you very much. I'm very happy to present here at ElixirConf EU stage for the third time. Previously I spoke in Warsaw and in Krakow. Krakow is where I came from today. Actually, there were another 4 speakers on the plane traveling from Krakow. So Krakow seems to be a European Elixir Valley. Over 5 years ago, I started teaching computer science at primary school. About 2 years ago, me and my wife, Anya, she's sitting over there, started a teaching practice aiming at educating girls in computing subjects. This talk is about our experiences. But may I first ask our audience if we have anyone who can code in at least one programming language? Nice, thank you. Anyone is raising at least one child? All right. Anyone tried teaching a group of people? Wow, I could not imagine a better audience. Thank you very much. This is exactly the audience I was hoping for. So we have programmers, parents, and teachers with us today. Very good. So teaching information and computer technologies at school started many years ago. Depending on the country or region, these kind of subjects had different names, different areas of focus, but probably most of you had a class with computers. Tried sending an email over the internet, created a slide deck, defined some calculations in a spreadsheet. Over time, as computer technologies evolved, so did the national curriculums. A national curriculum is a syllabus for a given subject, which is defined by the state, typically Ministry of Education. In 2014, England was the first state that introduced programming into the national curriculum and made it compulsory from the first grade. That is from the age of 5. Few years later, Poland followed and also introduced compulsory computing from first grade, which in Poland starts at age of 7. At present, not all European countries go as far as teaching programming from the first grade, but all recognize the importance of so-called computational thinking. And they teach it at primary school, earlier or later. Now, one aspect of computing teaching practice is particularly interesting. In England, in the upper classes of their education system, students choose subjects they want to study. If we look at the demographics of pupils who chose mathematics as one of their subjects, we see an equal split between girls and boys. Out of all pupils who chose maths, 50% were girls, 50% were boys. If we look at the demographics of pupils who chose computing as one of their subjects, we see that about 20% were girls and about 80% were boys. And that was in 2020, so some 6 years after computing as a subject was introduced to the national curriculum of England. Why is that? This is a question which is being actively studied across the world, and in recent years a number of research reports were published. But this trend is not specific to England. Let's take a look at the whole European Union. This map shows a proportion of women scientists and engineers in different regions of the continent. In regions in navy blue color, women represent more than 50% of scientists and engineers. Those are regions like Portugal, where we are here today, Spain, Bulgaria, eastern part of Poland, Lithuania, Norway, Denmark, Sweden. But in other regions, you can see that women represent various percentages. In many countries, not just in Europe or on all continents, the topic of how to promote a fair representation of societies in STEM subjects is actively debated. And so is the topic of what makes the computing pedagogy effective. In our experience, the computing pedagogy needs to consider age, because if we want to teach computing at the early years of primary schools, we need to consider how human brain develops over the years. So if our ambition is to teach so-called computational thinking, which includes algorithmic thinking, abstraction, decomposition, evaluation, logic, generalizing, and so on, we need to consider how skills, understanding, and memory are constructed in our human brains. In our experience, computers or tablets are not necessarily useful when teaching children at the age of 6, 7, or 8. Actually, electronic devices are often a source of distraction. Humans at this age develop their social skills. They start to relate themselves to their peers. They learn how to interact in a group. A group of researchers from the University of Canterbury in New Zealand exploited it and created classes where children play active roles. The project is known as Computer Science Unplugged. It shows binary system, sorting, encoding, decoding, protocols, many other computer science concepts. For example, the class about binary numbers uses a set of cards with dots. By flipping the cards, we can find the combination which makes a specific number of dots visible. In this example, to represent the number 9, we need to flip 2 cards up and 3 cards down. Children at the age of 6 often can count. They understand the operation of adding numbers. So they are perfectly capable of figuring out which cards to flip and how. In this movie, she was tasked to note down number 8 in the binary system. So you will see shortly how she came up to this one. Later in this class, she continued, and she had to represent her date of birth with zeros and ones. Your month, let's say April being your month of birth, your day being 20, day of April, being another number. So there's plenty of numbers that children at this age understand. They can relate themselves to those, and we can use those numbers as a problem to solve. Almost there. Aha. Okay. Another example shows how sorting networks work. In this diagram, each circle is an intersection of 2 paths where we need to compare 2 numbers. Numbers are traveling from the right to the left. When 2 numbers meet in a circle, lower number goes left, higher number goes right. Now you may wonder, how can children play roles in this scenario? We can see 4 numbers on the right. From the top, these are 3, 4, 2, 1. Now let the game begin. At the end, we see sorted numbers from 1 to 4. Teaching computer science unplugged for 3 years to different classes was an eye-opening experience for me. I was in shock when I saw a class of 9-year-old pupils who managed to design a communication protocol. It had splitting payloads into packets, packet ordering, packet loss discovery, and lost packet retransmission. All of this within 45 minutes, which is a single class unit in Polish schools. The protocol resembled some of characteristics of TCP/IP. It allowed transmitting messages in a noisy environment and had good quality and accuracy. 9-year-old. Already fearing about your job, don't you? I can see fear in your eyes. These experiences led us to establishing a teaching practice under the name koderki. Our aim is to teach abstractions by making. When designing a logo of koderki, we had an opportunity to hide a message which programming language we aim to teach. And this opportunity has not been missed. So, at our teaching practice, the questions we were asking: how do we teach computing concepts like recursion, conditional statement, loop, in an engaging way? In a way that will make children at the age of 10, 11 remember the patterns. In a way that will allow them to relate these abstractions to what they already know. Our brain memory is associative, meaning that we memorize things in relation to other things. So how do we exploit such characteristics of our brains when teaching computing? How to explain recursion? Where do we see recursive patterns around us? Fern grows in a recursive pattern. Trees grow in a recursive pattern. In maths, a fractal is defined using recursive functions. So maybe we can grow a fractal tree. This kitty, named Jovita after the first Polish female programmer, is growing a fractal tree in the picture. We used a simple recursive algorithm to generate fractal trees and let our students play with it. They could experiment on their own with the number of iterations, randomness, and other parameters. And this would result in quite realistic trees, as you can see in the picture, similar to those created by my Mother Nature. We then continued to explore patterns used by Mother Nature, experimented with real plants, used some artistic techniques to copy the patterns from plants to textiles. To make it a memorable experience, we used a technique of press printing. Every girl in our class made a custom backpack with a fractal tree. Here you can see how a fractal is transmitted with press printing to a backpack. Yay. So, of course, they could take fractal tree backpacks home, and we see them every now and then on the streets of Krakow. Those are very fashionable backpacks. Another example, how to make children familiar with code editing, compilation, debugging, conditional statements. So what we tried is the Ink programming language. It compiles to interactive books, and it is used in development of narrative games. Our class created characters, and then a whole story, and then a whole storyboard, which allowed us to capture how the story narrative can branch off. You can see that the storybook has several branches of the story. The Ink programming language compiles to an interactive book where the reader decides which branch of the story to take and how will the story develop. The end result of this making was published online, so girls could show their book to parents, relatives, or peers. So we continued our quest to find and try effective teaching methods. I already showed some successes we had with groups aged 7 to 9 with Computer Science Unplugged. I discussed experiences of working with groups aged 10 to 11 with the artistic makings. I used to chair the program committee of Lambda Days conference, and this is where I came across the Bootstrap Project. It was created by researchers at the Brown University in the United States. The project uses functional programming while teaching subjects such as algebra, data science, physics. They developed a very rigorous and engaging content. They approached it with a truly scientific spirit. Their content was evaluated with scientific methods, and they published a lot of academic papers and presented at various conferences, so you can read more about it. In Polish schools, on the subject of mathematics, pupils learn about numbers, algebra, sets, functions, geometry, probability, logic, and a few other topics. And inspired by the Bootstrap Project, we started to think about ways to exploit what students already know and what they intuitively understand. So we created a map of maths. It is supposed to help with mapping of math concepts to programming concepts. We took the Polish national curriculum, tried to identify all sorts of math topics like equations, trigonometry, theory of sets, function composition, and so on. We grouped them in lands, like in a real map. Then the second version of the map was created with generative AI and should make it more visually appealing. Each hexagonal space maps to a topic, but also creates a stylish world to associate a concept with some imagined faraway land. Remember the class about patterns in nature, which helped us explain what recursion is? Welcome to the world of ferns and other fractal patterns and plants. The world where girls who code use math and computing to make things. When mapping math concepts to computing, the functional paradigm is very handy because its foundations are built on mathematics. It is not to say that other programming paradigms are not useful, but some of them, like imperative programming or procedural programming, resemble the architecture of processors and machines that execute the program. When we teach computing with an imperative language, we first need to introduce new abstractions and teach patterns that are further away from math concepts. At schools, we already teach algebra and algebraic expressions. At the age of 7, we ask students to figure out all sorts of math problems, like, I had 5 apples, I ate 2, how many are left? We teach substituting a value into a variable and then evaluating an expression. At the age of 10, 11, it's students' daily job. We teach definitions of geometric functions like area of a square or perimeter of a triangle. All children at the age of 12 know them by heart. We teach set theory. Going from there is not far to get to complex data structures. So I showed the class about fractal patterns, which can help with the concept of recursive function. How would you imagine a land of pattern matching? I leave that exercise to our listeners. But this is where Elixir and Livebook come into play. Ever since Livebook was released, we saw many use cases, one of them being teaching. The use of math concepts in functional computing can be nicely illustrated with Elixir. You saw on the previous slide that math notation is close to Elixir syntax. Each tile of our hexagonal map of mathematics is implemented as a separate Livebook. So you can navigate. We don't teach computing by looking at the illustrations. These beautiful graphics just help to memorize and navigate. We teach through classes which are implemented as live books. They have rigor, as seen in the Bootstrap project. Without rigor, one cannot expect tangible teaching results. The Bootstrap project has a lot of good quality material about it, so I'm not covering it here, but if you are interested, they have a lot of good material and publications on their website, how they go about teaching. So there is just one more piece missing. Children need intrinsic motivation to learn something. If they are driven by our own interests rather than theirs, if they are driven by imposed conventions, their learning will be less effective compared to if they are driven by their own motivation. So we invite them to develop an outdoor game. The game has a number of riddles. Solving one riddle leads to another. So for example, the riddle requires to find out some number or calculate some value. Then this number opens a cache. Inside the cache, you can find a QR code, which takes you to the next riddle, and so on and so on. If you ever locked yourself in an escape room, you can imagine how it goes. Riddles can be deployed as the recently released live book apps. This way, a QR code can navigate to some online endpoint. And by the way, we tried deploying using a standard live book Docker file. We used Google Cloud Run service in a school classroom. Assuming that children can access internet, it worked very well. Cloud Run is a serverless offering from Google. We can set the timeout for up to 60 minutes. So we get an instance of livebook which lasts more than a standard class unit of 45 minutes, and it auto-destroys itself soon after. So Elixir with its ecosystem is very useful to teaching national curriculum. This is the message I wanted to send. I'm open for any questions if we have any. Thank you for your attention.
All right, we have time for a few questions, one or two. So if you have any, please raise your hand. Yes? I'm going to start with one. What would be your suggestion if you're starting to teach kids programming? Because you mentioned intrinsic motivation, but it's also, me as a parent, it's also hard because I like programming and I don't know if the kids like it. So I don't want to be too pushy. So what would be your suggestion?
If you are a parent who is already a programmer, you probably already know a lot of things by heart, and it's hard to imagine what is it that they don't know, what is it that they don't understand. The moment you understand something, you almost immediately forget how it was 5 minutes ago. So I would trust scenarios which someone already developed, tried, evaluated, got feedback, maybe improved. Those computer science unplugged classes are really, really easy to start with. You don't need to be a computer scientist, you do not need to be a programmer, and those scenarios, step by step, in plain English, guide you to how to run a lesson. Try it with one kid, then try it with 2, try it with 10, try it with a class of 20, and you will start to see how that goes. Mm-hmm. Yes?
Yeah, thank you. In fact, your answer segued to my next question. I have a daughter of 6 years old, and in fact, I want to understand. So we live in States. I want to see how I can start teaching her programming. And I looked at your website. I think it's in Polish. So I wanted to know, like, if there's any material or something that you give, and how do you kind of engage a larger community to adopt this kind of standards to teach kids at Engage?
So all the materials that we have used are open source. Yes, some of those were translated to Polish for the sake of classes we run, but you can find English equivalents. So like Computer Science Unplugged, English scenarios. Bootstrap, English scenarios. So you can start with any piece that we presented here using the English version of this material. And again, the website we use here is koderki.pl. It's more like our landing page to help us with some communications. So it's not where you will find it, but if you will Google any other project which was mentioned, you will easily find the homepage of respective projects.
Thank you.
Sure.
Okay, we also have one question online. Are there any examples of those live books publicly available?
So my intention is definitely to make them all open source and publicly available. For now, I am iterating on them with a group of girls that we teach every week. Those are not publicly available at this moment, but I will definitely make them open source at some point.
Yeah, thank you. One last question.
Thanks. Thanks for the talk, Michal. Do you think, in your opinion, is functional programming a better kind of programming paradigm for teaching than, for example, object-oriented paradigm? How would you approach those? Like, would you even do you include those in your classes?
So some few years ago, I was running a coding club. It was a club where we were teaching Scratch, Python, so the standard way of teaching computing as it is today. And I very quickly got to the point where I was hitting the ceiling, I felt. Meaning that how can I explain the global state in the Scratch setup? That this is not necessarily what you should be doing if this is like the only way to do certain things in a Scratch environment. By no means I'm trying to downplay Scratch, which does wonders to children across the world. But if you ask me on the effective practice of teaching, I believe that having the language we use for computing being close to the language we use at the math class is useful. So that's my take on it. And I am always open for a debate.
Okay, thank you. So that was all for the Q&A session. Let's thank Michal one more time.